Why is supercooling difficult to predict in phase changes? Imagine cooling water below its freezing point and still seeing it stay liquid. That's supercooling, and it's one of the most puzzling phenomena in thermodynamics. When you think about phase changes, you usually expect a clear point where a liquid turns solid. But supercooling throws a wrench into that idea. It's like the liquid is holding back, resisting turning into ice even though conditions seem right. So, why is predicting this so tricky? It all comes down to the process called nucleation. Nucleation is how a new phase, like solid ice, begins to form inside the liquid. To start solidifying, tiny clusters called nuclei need to form and grow. But forming these nuclei isn't straightforward. It depends on microscopic factors that are hard to see or control. For example, impurities or tiny defects in the container can act as starting points for nucleation. If there are no such sites, the liquid can stay supercooled much lower than its normal freezing point. Thermodynamics tells us that phase changes happen at specific temperatures, like the melting point. But supercooling involves the liquid remaining in a metastable state. This means it's thermodynamically ready to turn into solid, but the energy barrier to start nucleation is still too high. Overcoming this barrier requires a fluctuation at the molecular level, which is random and unpredictable. Sometimes a tiny disturbance is enough to trigger nucleation, and other times it isn't. That randomness makes prediction very difficult. Another factor is the presence of impurities or surfaces. These can serve as nucleation sites, making solidification happen sooner. But in pure liquids or very smooth containers, nucleation can be delayed significantly. The size of the sample also matters. Smaller volumes tend to supercool more because there are fewer nucleation sites. Larger samples might nucleate sooner but can also supercool if the conditions are just right. Materials with complex phase behavior add even more unpredictability. Some substances have multiple liquid or solid phases or intermediate states, which can change the way nucleation occurs. This makes it even harder to predict exactly when supercooling will end. In mechanical engineering, understanding supercooling is important for designing systems that rely on phase change materials for energy storage or temperature control. If supercooling occurs unexpectedly, it can delay heat releases or absorption, affecting system efficiency. Engineers need to consider the randomness and subtle factors influencing nucleation when designing these systems. So, the main reason predicting supercooling is so tough is because nucleation depends on random molecular fluctuations, metastable states, uncontrolled impurities, surface conditions, and complex phase behaviors. All these factors combine to make the exact point of solidification below the melting point uncertain in real-world applications.